Good, thank you. And let me actually record the course before I forgot. Okay, so let's get back to the business. We actually started two-dimensional diffusion. We discretized the equation. We have everything to write the code. And at the end of the class, I mentioned that it would be great if I can find someone to give us a demo of his or her work. So is there anyone who would like to give us a demo of the code? Is there anyone who has completed the 2D diffusion code and MATLAB?
Yeah, I did.
Good, Sean. So if you like, you can actually share your screen and explain the code and give us a short demo. That would be great. Awesome.
Can you see in here?
Yes.
Okay, so I made a code pretty much copying the equations and some of the loops that we did for 2D advection, but used the equation for 2D diffusion. The first part of my code, it just explains what it tells the user, prints out what the code does for the user so they know. Then I put in some default values just to make it quick, and the X and Y minimums and maximums, the number of intervals, the diffusion constants, and maximum time and a time step. And then I just arbitrarily picked a square-shaped initial condition area, and I just gave it a concentration of 1 and arbitrarily picked some coordinates for it just to start out. Then I just ask the user if they want to use the user-defined or if they want to input their own. And so I have some code that just asks them to put in their own. I have a while loop. Just I tell, okay, is parameter okay? No. If it's parameter okay equals no, then run through this loop, and it'll just ask people if they want to add their parameters or just use the default ones. That way I don't have to add them in every time I run this to debug it. So that's what most of this is. Then I have it, it's kind of crude, I just have it print out the, show me the values. That's why I have here each of the variables, x min, x max, and so on. And that just, because I don't have a semicolon after it, it just prints it out. The semicolon suppresses the printout. Then I ask the user, are these okay? They say yes, it doesn't go back into the while loop. If they say no, it'll do the while loop again. So then this is pretty much kind of copied and modified from the 2D advection code, where I define my dx, my x step, define my y step, and then define a kind of a one-dimensional array for x just to get the range of values. And I go with x max plus 3 times dx because we have to have the 1 extra just to make up for the beginning and ending of our interval. And then we have a ghost point on either end. So we have to add 3 to the x or the y. I come up with the number of time steps, add 1, because time step 0 we really are calling 1 in this. And then I zero out make a U matrix, but zero it out with the zeros command. Then I have it going and put in my initial conditions here, just a nested for and if loops to fill those up. I'm just asking if it's within that range that I defined above. Just put the initial condition value in there. So it zips through this. Then I have it do the contour just to look at the initial conditions, and I have it let the user know, have the pause command, so they have to hit a button to keep moving. Then I go into the calculation code where we first do the ghost points. So the matrix U from all the way the x value of the number of x intervals plus 3, that spot's equal to whatever's in number of x intervals plus 2. So basically the furthest one to the right, so to speak, is equal to the next closest one to the left. I do the same thing with the left side of the x with 1, the location 1 is really equal to whatever's in location 2 to define my ghost points, open boundaries. Same thing with y. Then I run through the calculation here, and here's the u is, u I j n plus 1 is that equation that we came up with the diffusion constants. I end my loops and have it plot it, and then it ends the program. So clear this, and then I'll run it. So I wasn't sure how else to get it to put up a figure, so I just used the figure command, and it spits out a window like this. It asks me if I want to use put in my own parameters. So I'm going to say no to use the default, and it's going to give me, spits out what I've put in there. I'm going to say yes, these are right. These right, yes. Then it'll plot them, and it'll plot the initial conditions here. So here's that little initial condition box that we made. Then I'll just press a key to continue it. Go back to it. So then there it is. Can you see the diffusion happening there?
Right, yes.
It's really slow, and it kind of turns into a circle as it spreads out. So it's that's about it. It just, I think I arbitrarily picked so many time steps, or so many times. What I found is that there weren't very many values of that, the kx times delta t over delta x squared that made this thing work. Like almost everything made this thing blow up. It would just get weird. And this, I just tried stuff until I found one that didn't blow up. And this is about it. I don't know why the values are what they are, why they work. I didn't go that far to try to figure that out. So this is about it.
Okay, great, Sean. Thank you.
Yep.
This is great. Yeah, the code is actually more appealing than mine. So you did a lot of creative codes in terms of putting the inputs in your code. So that is great. Thank you.
Yep.
And I think I checked your code. Everything looks fine, except the discretization of your space. I think you added 3 to the endpoint. I'm not pretty sure if you need 3. I think you need 1 in the backward and 1 to the forward. So I'm gonna explain it, but everything else looks great.
Okay. Thanks.
Thank you, Sean.
Yep.
Awesome. Okay, so let me share my screen. Is there anyone else who would like to give us additional demo?
I tried, but mine's not as fancy as that, so.
That's fine, okay. Good, thank you. Okay, let me go through the code. I'm gonna start from basically our 2D advection, and we'll try to just modify the code for 2D diffusion, okay? So let's share the screen. Okay, can you see my code?
Yep.
Okay, great. And let me increase the font a little bit so it's easier to read the code. I think this should be fine. Okay, let me see if I can borrow our lecture last week so we can follow just the notes. I'm trying to find the discretization form of 2D diffusion problem. Okay, So we talked about 2D advection, the ghost points, and we found that we're gonna actually, this is for forward scheme, we're gonna need ghost points for right and above of our space domain, and for discretization in terms of the second derivative, we use this scheme. It's called symmetric second order. Let's move on. This is a discretization for diffusion equation and the final form of the discretized diffusion equation, right? So in this case, we're gonna need these ghost points around my boundary, above, left, right, and below the domain. And let's see if we can modify our two-dimensional advection. This is what we actually wrote last week to two-dimensional pure diffusion. Okay, so in diffusion equation, as you notice, there is no velocity. However, we have another constant term, which is the coefficient of diffusion, right? Let me open up my code so I don't miss anything. Okay, I'm gonna just modify this to kx. This is my coefficient of diffusion, right? And then, as I said, the unit should be square meter per second, right? I think I mentioned that for this problem, you can basically just choose 2 square meter per second. And if I didn't say that, let's just try this value. And the problem we are working is exactly like our two-dimensional advection, right? So we have a square domain. There is some pollution, impurity in our system. Everything same in terms of initial boundary conditions. We're going to just shift this from 2D advection to 2D diffusion. And then we're going to have another coefficient. This is our coefficient of diffusion, but for the other direction. So this is coefficient of diffusion in X, and exactly the same thing for coefficient of diffusion in Y. And let me change this to FTFS to the diffusion. And this is also diffusion. Okay, and nothing would be changed in terms of X min, X max, number of even space intervals. These are all the same. Time, exactly the same. Discretization in X, the delta X would be same. But then this is actually the part that Sean modified this, and we have to modify this because this is about the discretization in space, right? So as you see from the left figure, we're gonna need actually a ghost point. I'm trying to discretize the domain in X direction, right? We're gonna need a ghost point right here, my physical points, and additional ghost point on the right. In my 2D advection, from the FTFS, if you remember, we got actually just only one ghost point in X direction in right side, right? And as a result, there would be just plus delta X for my ghost point on the right side of the domain. However, in my 2D dimension diffusion problem, I need 2 ghost points, so 1 for the backward direction and 1 for the forward direction. So this discretization will be started from x min minus dx, which is this point, the coordinates of this point, the coordinate of the last ghost point, and then by these dx it will generate all these grids. Same thing for the y direction, right? Again, we have ghost point under my domain and ghost point above my domain. So you can actually modify this minus dx and plus dx for ghost points. And same thing for the y direction. And nothing would be changed in terms of time, right? This is just time discretization. It would be same. For unknown function, however, this is different, right? So in 2D advection, how many physical points you had? Nx plus 1, right? And remember that nx, this is number of intervals. This is a number of nodes, right? So for example, in this simple domain, nx would be 1, 2, 3, and 4 intervals, right? So the number of physical point would be nx plus 1, 4 plus 1, which means 5. And then we're going to add one more in 2D advection to take the ghost point into the consideration, and then as a result we're going to have nx plus 2 and ny plus 2. Here we're going to add one more, right? But actually we can write like this: nx plus 1 for physical point, one more for the ghost point on the left, one more for the ghost point on the right. And same thing for the y direction, right? So it's going to be at the end nx plus 3. Nx plus 2, nx plus 1 for physical grids and plus 2 for ghosts. Any questions so far? Good. And then these are all the initial values at before starting any approximation, right? Everything is going to be 0 at this moment. But then for initial conditions, we're going to put some initial values. As I explained in our specific special problem, we had kind of a square pollution in our system, so this is how we define it, and there is no need to modify this code, maybe a little bit, because we're gonna have nx plus 3, right? So we're gonna have nx plus 3, and the code will automatically recognize if the coordinates of this index is larger than 40 or less than 60, and then it can initialize the value into my unknown function or matrix. Okay, let's move on. I just deactivated this section. This is just to generate the video, so we don't want to make the video again. You know how to write it. And actually, for the next assignments, I would like to see your videos as well. So if you can generate the video and upload in your assignments, that would be a plus. Okay, let's go to the FDM approximation through our loop system. Number of time steps wouldn't change. The ghost points, actually, this is something that we have to modify. Let's see what we have. We have a ghost point on X in the left side and right side. Let's just make the right side correct. So because the total number of our grids are now different, we have to modify this to nx plus 3. So this is my very last point, right? So in the left figure, I'm trying to present this with my mouse. So this is the very end point, and then the index would be nx plus 3. So this point should be equal to the previous one, right? So I have to also modify this to nx plus 2. This is the ghost on x direction, I would say at right, or at the end. Okay, let's modify a ghost on y direction in above my domain. Again, same thing would happen for y direction at above. And then, as you notice, I'm gonna need some additional ghost points for left and below, right? I'm gonna start from the very first one. So the index of this one, what would be the index? What should I write instead of nx plus 3? This is ghost on left. What should I write in this position? What is the index of this ghost point? I'm still waiting.
Would it be maybe nx minus 1 or?
So nx is the number of intervals, right?
Yeah.
So I'm asking actually about the index of the very first column. What would be the index in terms of x? The first one.
Just minus 1.
Minus 1, which, as I explained last lecture, actually in MATLAB, we cannot have anything less than 1, right? So everything should be integer numbers and starting from 1. So we're going to shift this to 1. This will be 1, right?
Okay.
So this is index 1. And if this is index 1, the very last one is nx plus 3, right? Okay, so very first one, this should be equal to, what should I write here?
Two.
Thank you, exactly. So if you have answer, please just unmute and say something. And same thing for y, right? Did I put, okay, this should be 2. 1 and 2. So these are the ghost points on x direction and left and below for a start. Okay, marching in 2D space. So in previous case, we used and forward in time and backward in space. So in this case, this is a 2D diffusion problem. So it's gonna be forward in time always because it's, we are interested to calculate this unknown function for the future. But in 2D diffusion, we found that this should be symmetrical second order approximation, right? So it's not backward, it's not forward, it's just symmetrical, right? Okay. So what should I write here? So again, remember that marching would be happen only for physical points. Can you tell me how should I modify this? What are the physical points?
Could it be from n to nx plus 1 to nx plus 2? Because we have 3 points. Plus the ghost.
Not really.
To nx minus 1, right?
nx plus 2, this is correct. But what about the first one?
It would be from 2.
2, exactly. Thank you.
Yeah.
Yeah, just look at this figure, right? We are trying to just take into the account the physical point. So it should be, this is 1, right? This should be 2. And very last one, this one is nx plus 3. So the last physical point in nx is nx plus 2, right? And the same thing would happen for the y direction, right? This is 2, 3, 4, and then the very last one would be ny plus 2. And the formula would be, of course, different, right? This is a formula and approximation, find a different approximation for our diffusion problem. So let's rewrite it from the beginning. This is my unknown function, ij, next interval of time. This should be equal to my unknown function in ij and my current time. plus kx. Is that fine? Yes. And even if you write with a capital K, it cannot recognize it, right? So kx times my delta t. Did I write it in this way, or no, dt, small dt. Okay. And then this divided by dx power 2, right? So this is my equation. Because this is a second order partial derivative, I'm gonna have actually a power 2 of my space interval. So this entire constant will be multiplied with this bracket, right? Let's see what we have. We have u, I plus 1, and j, and my time would be current time, of course. I'm gonna just copy this. Minus 2 times my central point, right? And then plus my point in the left. So right, center, left. This is my entire first term, second term in my equation. Let me see what's happening, what's wrong with this parentheses. Okay, this is, I don't need this one, okay. This should be fine, one more. Okay, this is, and it seems that I don't need the very first one. Okay. I'm really confused with this parentheses. Okay, let me write from the beginning. Okay. Oh, I think because we didn't have any semicolon, I'm gonna receive the error. This should be fine. Okay, and then plus my second term, which will be exactly the same thing, but different parameters, right? So this should be ky, dt, dy, and then marching would be on j direction. So j plus 1 and j minus 1. And we should be fine. Okay. So this is about marching in 2D space. And we already defined the physical points. We have all the contours, and we should be fine. Let me check again this one. I think something is wrong again. This is killing me. Okay, so we close this parenthesis. This is closed. Okay, we need one more. Okay, this is closed. Nice. What about this? This is closed. And we should close this one too. Okay, now it's fine. Finally. Okay, so let's run the code and see what would we get. Again, we're gonna expect some diffusion. There is no bulk movement of the pollution. It's just diffusion in different directions, right? Okay, so some instability in the system. Let me pause my simulation. Let's see what is happening, what is wrong. I'm wondering about these NX. These are pretty small, so let's just put 1000, or let's just decrease the time intervals. Okay, so this will give us more, I hope, accurate result. Let's see. A little bit better. what if I change this to 1000? One more. Okay, this is not stable. I'm gonna pause this. I think there is something wrong in the code. So let me check with what I wrote before. I think there should be something wrong. And then my program crashed, so I have to open MATLAB again. Just a second.
Hey, Professor, while you're reopening MATLAB, do you remember off the top of your head the command stops the run of the program?
Yeah, Control and C. So
Control
this will
C.
stop. Yeah, but if you are actually during a loop, you can actually click on the right tab that after you run the program, there would be a pause, so you can pause it.
Okay. Thank you.
Yep, no problem. Okay, so let me see what's going on. I think there should be something wrong. This should be fine. This is fine. Good. This should be nx plus 3, of course. Initialization should be fine. This is nx plus 3 plus 2 plus yes, plus 3 plus 2. This is good. And in terms of the first close points, this is also fine. So I don't see anything wrong in my close points. There should be maybe something wrong in the marching. Okay, let's see. It's kx times dt. This is power 2 ui plus 1 minus 2 times, oh, okay, so this is a problem. So I messed up with the parentheses again. This should be 2 times my uijn plus my u. Okay, let me actually remove this and write everything from scratch. Okay, this is fine. Minus 2 times my unknown function in central point, ijn, and then plus ui in backward direction, j and n. And now I can close the parentheses. Okay, this is much more better. And then let's take a copy for the entire thing. And modify everything for y direction. So this is gonna be I, j plus 1. This is the same for a center point, I, j plus 1. Semicolon. I think this should be stable. Again, my MATLAB crashed. Okay, the problem is I'm opening at least 20 pages in front of me, so this happens sometimes. Let me close my MATLAB. Nope, I don't want to send the report. I hope it will not happen again. Okay, so let's see if we save all the changes. Yes. I think this should be fine. Let me run the code. I'm gonna just remove, decrease the number of intervals in space so the program wouldn't crash again. Start. Okay, this is much better, right? So we are getting some diffusion. It's a little bit going to the left, which is not correct. Let's pause the program. We're going to increase nx and ny a little bit to 200. Let's see what would happen in this case. It seems that I'm not lucky today. Okay, so one more. This doesn't look good. Something is wrong with the code again. And this is how actually you come up with the debugging, right? You just check the simulation result and you can find that something is wrong with your code. And I think it should be in terms of discretization. Okay. Can you tell me what is wrong here?
Well, I was going to say, wasn't there something weird you have to do when you want to square a term, like period squared?
Squared. You're talking about. Mhm.
Yeah, when you raise something to the second power, you said last time we have to. It doesn't like it if you don't put a dot or something. I don't know.
Oh no, that's fine actually.
Okay.
If the program doesn't give you any error, that should be fine. But there is actually something wrong here which I can't see, but I'm trying to.
Well, that was just literally my only idea. So.
Okay. But can you tell me which section is wrong? And that would actually make a little bit of advection to the left side.
Oh, I minus 1 should be j.
Exactly. Thank you, Khaled. Yep. So the last one, this should be j minus 1. Above, center, below, right? And I hope that this time we're gonna get some actual diffusion. So it's not moving, it's just diffusing to the other points, right? So what is I don't like about this contour is that, as you see, the axis or the colors are changing based on the maximum value that you get through the approximation. So it's changing from 1 to 0.5, and then because this is an animation, it will not give you exactly what you like to see. So I'm gonna pause this program and teach you one more trick or technique. Yeah, probably I have to shut down my desktop for a couple minutes and then reboot it again. But this is the code actually. So if you type c-axis, it will define the value on your contour. So now, as I said, it will basically change or tune the maximum number based on the maximum value in your matrix. But if you type c-axis, then you can define the minimum and maximum value on your contour. Okay, so if I run this, you see that the value wouldn't change again. And this is consistent with the next diffusion contour plots.
Sorry, can you just repeat why you did that?
Okay, so let me actually pause this. Quit. So if I actually deactivate this, right, and run the program, so just look at the values, right? They're changing, and the maximum value of the contour or the color that it's plotting on the contour will be based on the maximum value along all the unknown functions that you have in your matrix, right? Because it's diffusion, of course, the maximum value is diffusing, right? And then the contour is tuning its value based on the maximum value. And I don't like to change the colors, right? I like to fix this for a certain range and see what would happen in time. And that's how you can actually write this code to set some minimum and maximum values, and this will be constant for the entire simulation. So the color bar wouldn't change anymore. Okay. Does that make sense?
Yeah, thank you.
Okay, no problem. So one more technique. This is contour, and other way around, you can actually plot your final outcome in terms of three-dimensional surface or surf code. So instead of having this contour, I'm gonna just deactivate these contour lines and teach you one more trick. So let's say we're gonna just write surf. Your final outcome or visualization would be in terms of a three-dimensional, visualization. So surf x, y, these are discretization in x and y, which we already did. So you are providing the coordinates of x and y, and then your unknown function. I like to plot everything for this time step of n, right? This is my current time step, exactly like what we did for contour. Close this. The edge color, this will provide, let me actually remove this. I'm gonna explain this later. Semicolon. So like the axis for the contour, you can actually define the limits of the z-axis because this is a 3D surface. So we're gonna write just z limit, and then I'm gonna define exactly the same thing that I did for my contour, right? So for contour, everything is in terms of different colors. 1 for red, for example, because we are using the jet color map, and 0 for blue. Here it's actually trying to plot this in three-dimensional view, and then you're gonna have some heights, right? So the height in this case, 1 would be for the highest concentration and 0 for the lowest. Close this, and like before, show the graph. Thing we should be fine. Let's see what would we get out of this program, and I have deactivated this one. Okay. So this is my plot, right? So you see a lot of black lines, right, around my plot, which is annoying. I don't want to see the lines, right, or the edge colors, which is black in this case. So I'm gonna remove the black edge color. In this case, you're gonna just define this format, edge color. This is the default value, right? But I'm gonna change this to none. So this is the final visualization. So you see that at the beginning we had this about 1 concentration in your square, and it's diffusing to other regions in your domain. This is beautiful. I like this presentation. And you can do the same thing for advection, right? And if I just plot this surf for just the moment, the first moment, which is my initial condition, and let's just pause the program, we should get a square, hopefully. And this is my square, right? So even you can, once your program is stopped, you can actually use this rotation 3D tool on the right and play with your map. So you have a lot of freedom. This would be better if you pause the program during the diffusion. So let's just do this approximation for 50 steps. Okay, so this is stopped, and then I can play with the view, right? All right. So actually the main goal of this lecture or course is not teach you all the tricks and techniques in MATLAB, but at least I think it's going to be good to talk about some of these techniques, which would be really helpful in your future assignments and projects, and maybe for your future if you like to write more codes in MATLAB. Any question? Nope. Okay. So one more thing that I would like to give you about writing code in MATLAB is that, so at this moment I'm just working on a very simple 2D pure diffusion problem, right? And then we have about 80 lines. For 50, 100 lines, that's fine. But once we are moving forward, working with more complex problems, we may end up with, writing codes for about 200 or 300 lines. Well, this is clean. We have defined different sections. We know how these sections works, but this is not really professional. Okay, so the way that the people that are writing codes for simulation, they write the codes is that we're gonna define some functions or so-called subroutines and put each section under a specific function. And what does that mean? For example, I have different sections, right? And each section is responsible to do something special, right? This is discretization, this is for initial conditions, and so on. So function or subroutine is like a machine. You feed the function with some input, and then it will return you some output. Okay, so for example, if I like to write a function for this section, my outputs are basically these variables which I'm trying to calculate based on some input variables, right? So dx, x, dy, y, n steps, and u are my outputs. My inputs, these are some variables that are predefined. So how to write a function and how it would help us is that I'm going to actually remove all this section, right? And then just by calling the function, I have to just write one line which would call the function. And this will actually save a lot of lines, and it will give us a very clear coding side. So let me teach you how to write the function. We're gonna just create one more script, right? So click on a new script, and then you can write your function. Start writing a function. So we're gonna start with this script function. You have to actually put a bracket. Inside the bracket, this will be my output. So I'm gonna fill this with my output. This should be equal to, you're gonna pick a name, and this name, whatever you like, but it should be actually close to what you're doing, right? So for example, I'm writing a function for discretization. So let's just call this discretize. This should be, I need to change this to discretized. Discrete func, right? Discrete function. You open the parentheses, my round brackets, and inside this it should be your inputs. So let me just copy and paste the entire section, put it here, right? And then you have to type this script return. So the function knows what are the inputs, what are the outputs, and how to return the function, the variables. What are my inputs? It's x max, right? I need to have the x max. I need to have x min. I should know nx, right? What else? Dx should be fine because we are actually calculating dx at the same function, so we don't need to put it in the input. For dx, again, the same thing. dy should be fine because we are already trying to calculate these n steps. We need tmax for n steps, and that's fine, right? We have everything. So what this function is returning is dx is returning x, dy, y, n steps, and u. And then click on save. So the main program, this is my main program that I'm trying to write all the functions in it. I saved this in a special function folder, sorry. Right, so
Sorry to interject, but I think you missed dt when calling for the input parameters.
dt, exactly, thank you. That is correct. So tmax and dt. Okay, so this function, this is my main function, right? And then I'm gonna have some children or sub function or subroutines. My main function, let me see what is it, the location. It's lecture 5 MATLAB, and I have to save my new function at the same folder, which is in the same folder. So this is important. The name of the file name should be exactly equal to or similar, no, not similar, it should be the same as the name of your function. So discrete func, that is fine, save, right? And then how to call this in your main function. Just copy the first line without the function. You don't need this script. Go to your main function. I don't need this anymore. And just type this, right? So what does this doing? It's just you are fitting this with these input parameters and then returning output parameters. I'm gonna stop my program right at this point to see if this is working in a good shape. And you see, I received everything, right? So y is returned, dx is returned, dy is returned, everything is calculated in your function. And you can actually do this for all these different sections. And you can imagine at the end, instead of having these 80 lines, you would have just 4 or 5 lines, right? And your code would be much more clear. Is this clear? Do you have any question? Okay, so we already talked about 2D pure advection, 2D pure diffusion. I think you can work on advection diffusion problem yourself, so I don't cover this, at least in this lecture. I like to move on to Laplace equation, which should be more relevant to C-page problems. Okay, so if no question, let me close my MATLAB. And explain a little bit about this C-page problem. Okay, so this is basically the lecture from my soil mechanics class. I think that would be good to cover a little bit on the background of this seepage problem. We're going to work on Laplace equation, which is the basic of seepage. Not only seepage, it's also about heat transfer problems, right? But the steady state. So I hope that you still remember these flow nets. Well, some of you are not from civil engineering department, so let's give you some insight about this subsurface flow analysis. We have different dimensions in flow systems, right? One-dimensional flow. Well, we can assume that the velocity of our water molecules or fluid molecules, these are the vectors of velocity are all parallel and equal in magnitude. So we have a one-directional flow. A two-dimensional flow, this is when velocity vectors are different in direction and magnitude. And of course, we're going to have some three-dimensional systems. This is the most general flow problem. And in most cases, of course, we're going to have 2D or 3D problems in reality. One famous example would be seepage under embankment dams, right, or concrete dams, or any groundwater seepage problem. So in this case, we're going to have some upstream, some downstream, and upstream. Of course, the pressure head or total head of water is larger. And let's see, this is the cross section of my dam, upstream, downstream. And I can represent this in two-dimensional problem, right? So how water moves inside my soil or subsurface, that's a question, that's a mystery, and it's gonna be something like this, but then the question is how, right? And how to solve this flow problem, which would be from Laplace equation or Laplacian equation. It's all about seepage of water or fluid through this permeable soil. And of course, we're going to have some impervious problems, sections. So from continuity, actually, we can derive this Darcy's law in one-dimensional flow. So imagine that I have a long tube, right? In one point, I'm going to have some higher energy or higher head, pressure head, and on the other point, I'm gonna have some lower energy. Although actually the direction of my pipe is from, a lower depth to a higher depth. So you may say that we're gonna have a flow from right side to the left side, right? But it's not just like that. It's not just about the gravity. It's just about the energy of water or the total head of water. So how to get this total head? We're gonna use some piezometer, put the piezometer, the level of the piezometer, right? Or the depth of the water or fluid in the piezometer, this will give you the pressure head. We're gonna have some reference line to take into the account the gravity, right? And by summing up these two values, I can calculate the total head or total energy of my fluid at this specific point, right? So HA, this is my total head at point A. For this specific point, point B, this is my total head. And as the total head of A is larger than B, I'm gonna have a flow from higher energy to lower energy, right? This is about a continuity. So how does this, where does this Laplace equation came from? It's all about the continuity. So let's imagine that I have a small element inside in the soil. I should have some flow in, right? This is my flow rate. Some flow rate from X direction in, from Z direction in, and of course I'm gonna have some output flow. So whatever in, it should be out of the system, and this is all about continuity. From Darcy's law, we already know that the flow rate inside any permeable system should be equal to your velocity times the cross-sectional area of your system, right? So for example, here, if I know the velocity of your fluid, just by multiplying this with the cross-sectional area of the pipe or the soil domain, you can calculate the flow rate. So let's see if we can derive the Laplace equation from the physics, right? So we didn't really, in previous lectures like 1D or 1D or 2D advection or diffusion, we didn't cover where does these physical partial differential equations come from, but this is something that you can get insight about, at least for a Laplace equation. So continuity, in, out. So I just substitute my flow rate with velocity times the cross-sectional area, right? Remember, flow rate is V times A. In X direction, I'm gonna have Vx. So what is the cross-sectional area of this point? If you look into a three-dimensional view, right? This is my cross-sectional area perpendicular to the direction of the flow, right? So this area should be dz times dy, correct? Same thing, opposite direction. This should be vz, velocity in z direction times the cross-sectional area, which should be dx times dy, right? So this is all the flow in. But what would be about the flow out? We're gonna have some change because of the change in the velocity. This is about the energy dissipation in your system, right? Energy dissipation or adding energy, depending on from which point we are moving to the other point. But this is all about the seepage problem, right? We have some permeable system, it has some conductivity or permeability, and we're gonna lose some energy through this movement of fluid. So this is a term of the change of velocity or loss of the velocity. And then if we write everything from the continuity, we know that this should be equal to 0, right? So the summation of all the Q outs minus the summation of all the flow rate in, this should be equal to 0. Rewrite everything. A lot of these factors would be actually cancelled from each other. So for example, these two, this will be cancelled with these two terms, right? And let's see what would be remained, right? This is the equation. This is all about velocity, right? But Laplace equation is about the head or total head. So V, my velocity is equal to my permeability times, do you remember what is this term, I? Okay, the question is, what is this I? Velocity is equal to permeability times.
Is that the hydraulic gradient?
Hydraulic gradient, exactly. Thank you. This is the change in total head divided by change in the length, right? Or total length of your system. But anyway, if you rewrite the velocity for the permeability, then we see this term, and then the final form of the seepage is this guy, right? So this is my permeability in X direction, permeability in the Z direction, and H is my total head. So this is a final form of Laplace equation. If my soil is isotropic, it means that the permeability in X and Z direction are all equal. Then this will be cancelled because you can divide everything with Kx or Kz, and this is Laplace equation for isotropic system. So through this Laplace equation, we can really answer this mystery, right? So the solution to Laplace equation will give us this head. This is my unknown function, right? So we can write this in our general form. So instead of h, you can write u. This is my unknown function, but we know that this is our total head. There are some specific points for this problem. I have upstream, downstream. There is an impermeable wall between my 2 points, right? And then if I put a piezometer on this special point, this is a known, this has actually a known total head. Because the level of the piezometer would be stand exactly right on my upstream, right? So this is a special point. And the same thing would happen for my downstream point. So these are the point that is exactly located on my downstream. If I put a piezometer, the level would be exactly on the downstream. And this is saying that I'm gonna have a head loss from upstream to downstream, right? And the head loss is exactly equal to the subtraction of my total head from A to B. So can you tell me if I put a piezometer on point C, which is this point, what would be the level of piezometer?
Somewhere between the two.
Exactly, somewhere between A and B. Sorry for this piezometer, which is not having the best shape, but we should get somewhere here, right? This is all about the energy. This is a max energy, mean energy, and this means that I'm gonna have some movement from higher to lower energy. But the question is, what is actually the level, right? This is a mystery. So if I put the piezometer, it will be in between. And of course, I'm gonna have some flow field from upstream to downstream in these shapes. And what is really interesting about the movement of fluid is that this is really depend on the geometry of our problem. Let me see if I can clean. Okay, let me actually plot another geometry. Let's say instead of having this wall, then I'm gonna have something like this solid section, which is impermeable. So the geometry of your subsurface, of course, it will make a lot of change, and in this case, the movement of the fluid will be derived from the shape of your geometry, right? So the most common solution to Laplace equation, this is what most of us actually learned through the flow-net solution. And I briefly explained this during the soil mechanics lecture that there are some numerical solutions like this finite different methods. We never had a chance to work on it, but we will in this lecture. So we're gonna have some constant head. The total head will be constant at any point located on the same equipotential line. So remember this term. What does that mean? It means that the points on these lines would have exactly similar total head or energy, right? So for example, one of the, yes, go ahead.
I was going to say it's the seepage line where the energy is equal.
Could you repeat again?
I think you answered it. I was going to say the seepage lines.
Okay, seepage lines. Yeah, seepage lines are different. Yeah, exactly. So this is equipotential lines, right? So equipotential lines, these should have similar or same total head or energy, right? Seepage lines or flow lines are exactly the opposite. This should be perpendicular to the equipotential line. So I'm going to talk about it. But yes, the previous one, these are the seepage lines. So can you tell me what is, or can you point to me some equipotential lines in this figure on the left side? So this is the first equipotential line, right?
The ground is also one.
Yeah,
Yes.
that's right.
Exactly. So the ground on the upstream, because if I put piezometer of the points, in all the points on this ground point, they will stand actually at the same level, right? So this is my first equipotential line, and downstream we have the same thing, right? What else? Well, if I put a piezometer right at this point, I could actually find some other points which they should have actually the same total energy, right? And if I connect all these points together, this is my second equipotential line, then the next one, and so on, right? So can you tell me how many equipotential lines in reality we have? Let's say this is a real problem.
An infinite number?
Exactly. An infinite number, because we are just talking about, you know, infinite number of the molecules of water, right? So there is no such a term. There is nothing in reality that we can actually say we have 10 or thousands of equipotential lines. These are just some artificial numbers that we made to make our problem just more simple, right? So again, from higher energy, and these are actually the color meanings, from higher potential or high potential to low potential, right? So these are my equipotential lines. In opposite way, we could have some flow lines, right, or streamlines, and these are exactly perpendicular to your equipotential line. And why is that? Because the flow should basically move from higher to lower energy, and this will define the direction of your flow. So can you tell me what is the shortest flow line in this figure?
The one underneath the wall immediately.
Exactly. So this is actually my shortest path for percolation or flow line. It's gonna, so this water molecule will start from this point, try to percolate to the downstream, right? What is the longest flow line?
Should be the farthest. Right.
Say again?
Should be the farthest from the wall.
No. And this is an infinite problem, right? So let's say these are extending to right and left to infinity.
Is it the bedrock?
Exactly, thank you. So this should be, this is going to be extended to infinity, right? So you can actually imagine that I would have a very long flow line from my right, my left, boundary to the right boundary. But because this is infinity, then I'm gonna have a flow line right on my bedrock. And so you're gonna have actually more and more flow lines. And like the equipotential lines, you're gonna have infinite number of flow lines, right? So in FlowNet solution, and that's why we had to actually shrink the number of flow lines and equipotential lines to just a few one, right? So in this case, you can calculate the area of each section and then try to calculate the flow rate and at the end, the permeability of your system. But today we're gonna learn actually how to accurately simulate this through finite difference approximations. Any question? Okay, so let me see, what is the time? It's 6:40. Okay, so let's have about 10 minutes break. And as I said, if you can go to your bright space and complete your evaluation, I really appreciate it. Thank you guys. I'm gonna stop my video and share screen. And we'll be back about 6, let's say 50. Okay, resume. Okay, one thing that I wanted to mention was actually I received, I think, 7 evaluations, so maybe it takes more time. Again, I appreciate if you can complete your evaluations before the deadline, which is, I think, in 2 or 3 days. Anyway, I'm not sure if you had the chance to check this textbook that I uploaded on Brightspace. So if you check the textbook, let me see, my pen doesn't work. Actually, you cannot see my screen. Okay, just a second. Okay. So if you check this textbook, Cousin and Mingham, this is a nice book about finding a different approximation. If you check page 30, not 32, 23, you have a nice table. It's actually have all the partial derivatives that you need and all their finite different approximations. So let's say we have partial derivatives for our unknown function for x, for t. It can be second derivatives or anything. And then you have actually the finite different approximations in terms of different types, whether it's forward, backward, central, symmetrical. So it has a nice summary of all those approximations. I think up at this moment you should be able to realize or remember all these approximations by just top of your head, because I think that's really easy because they have some type of intuitive meaning. Like forward approximation, we know that we have to use the next point, right? So in this case, we're gonna have I plus 1 minus I ui, right? So this is the next one, this is the previous one, and this should be divided by just one interval, right? For backward, again, the same thing. For central, that this should be from the 2 steps back or forward and divided by 2 delta x. So I think that should be easy to memorize all these finite different approximations. Anyway, please take a look into this textbook. It has a lot of examples and nice other problems about FDM approximations. And this table is a nice one just to have for writing your codes. Okay, let's move on to our actual topic, which is about Laplace equation. So we're gonna focus on C-page problems, but it can be actually applicable to heat transfer problems, 2-dimensional C-page. And does everything looks good? My voice, screen, everything? Just to confirm before I move on.
Yep.
Thank you. Okay. So my Laplace equation is in form of second derivatives of a known function with respect to x. I'm gonna just write it in y direction. It doesn't matter, you can just write z or y, doesn't matter really. And this is equal to 0. This is a very specific form, and which means that my soil, subsurface, or material is isotropic. The general form is that I'm gonna have some conductivity with respect to x, And this can be different from the conductivity in the y direction, right? So in terms of the problem that are involving subsurface, like geological formation, rock or soil, anything under our feet, or geomaterials, this should be in terms of a stratification of soil, right? So for example, if this is my ground, let's say again I have some impermeable wall, and this is my upstream, downstream. I'm going to have some movement of water, but then depending on the stratification of soil, right? I might have different soil layers, and even for each soil layer, the permeability in X direction would be different from the permeability in Y direction. And it means that water do not move at the same velocity in X and Y direction. So that's the whole point for this non-isotropic system. This can be again applicable to seepage or even heat transfer, right? In case of heat transfer, this term K is the conductivity of, thermal conductivity, right? Or heat conductivity. So let's say if I have a plate like this, my material, it would have actually different conductivity in different directions, depending on what type of material I have, right? So this can be applicable to heat transfer. Sometimes instead of having this 0, I could have some constant value, which we call this source term. So what does that mean? In our problem, our famous problem of flow under impermeable wall, sorry, I'm gonna have I would have some condition that, let's say there is a pump, and then this pump is connected to somewhere inside your soil, right? And then you are extracting some water out of the problem. So all these unknown function inside your soil, these are you, but then right at this point there is some source point, and this is actually extracting the water out of your system. So this is a kind of a source term. It could be other direction, right? Let's say you are pumping water into the system. So in this case, it will generate some higher energy inside your domain. So we could have actually some source term in our seepage Laplace equation, but for this lecture, we're going to just talk about the general form without the source term. So what is special about this Laplace equation is that this is a steady state, right? There is no time involved in this equation, but there are actually some Laplace equation. This is not Laplace equation anymore, but on a steady seepage problem, right? So if we write on a steady, it can be in the form of kx. Again, the same thing. Let me clean this. This is steady, and then the unsteady form. Of course, we're going to have some time involved, right? Because our unknown function would change in time. And this should be equal to the change of your unknown function with respect to time with some new term for, at least for the seepage problem. What is a C? This is soil mass specific flow. And if you are going to work on the heat transfer, this should be soil mass specific heat. And this term is basically the density of your soil. So isn't this equation familiar to you? What is this equation?
Diffusion.
Exactly. So this is pretty similar to diffusion. It's actually diffusion, right? It has just some new term for unsteady seepage problem. So we're gonna work on that in the next lectures. Okay, let me resize that part. Our focus for this lecture would be only on this type of a steady state Laplace equation, isotropic or non-isotropic. So one of your projects would be actually on this steady state problem with having a source term. I think it's going to be a fun project. It's about an island, basically. Let's say you have an island. I'd like to give you some insight about your projects. Let's say you have some nice coconut trees on your island. And it's isolated in a lake. We're gonna actually build some facilities on top of your ground on your island. However, because this is a fully saturated soil, right? So let's say if I plot this in plan view, this is your groundwater table or lake level. This is your island. And this is your soil, of course. The level of the water should be exactly equal to the level of water in your lake, right? This is a steady-state problem. And as I said, we're gonna build some facilities on top of the island. However, to build the facility, we have to make the foundation. And this is not good, right? Because the level of water is pretty high, not good for the footing. We have to make it lower by using some pump. So we're gonna use a pump, push the pump into the soil, and then extract water and pump it to the lake. Right, so in this case, the groundwater table would change. It should be something like this, right? And then your project would be how many of these pumps with how much flow rate you need to basically lower your groundwater table to a specific point. It should be satisfactory to make your foundation. So this is one of your projects. Just keep in your mind. That would be a nice project, I think. Let me move on. Let's try to discretize our Laplace equation. Okay, so discretization. Let me just write the equation, and then I need your help. I need somebody to tell me what is the approximation, discretization of this Laplace equation. Okay, I'm going to start with kx. Can you tell me how to discretize the second derivative? And remember that for second derivative, we're going to use just symmetrical approximation, right? Okay, I need a volunteer. You just did the same thing for diffusion, right? This is exactly like discretization for diffusion. So U
I plus 1 minus 2 UI.
exactly,
And then plus UI minus 1J.
I minus and J, right?
Yeah.
Okay, thank you. And then divided by
Delta X squared.
exactly. Thank you. And then almost the same thing, but in y direction, right? And this should be I, J plus 1 minus 2, U, I, and J. This is the central point. And then the point on the below, right? J minus 1. This should be delta Y square. Okay, so let me actually write everything for this guy, U, I, and J. So what I'm trying to do is to calculate the unknown function for the center point. Okay, so if I write everything in terms of U, I, and J, it's gonna be 2 U, I, and J divided by delta x2 plus times actually kx plus, and actually I take out this guy, right? Plus the same thing, but for y direction, ky, and I transfer all the other variables to the right side of my formula. This should be kx divided by delta x2. I already take out all the center points, so it should be just ui plus 1j minus ui minus 1j. Plus the same thing in y direction. J minus 1. Okay, so let's say, let's work just on a specific case. Okay, the specific case is that we're gonna have an isotropic system. So this is isotropic. It means that kx is equal to ky. First condition. And second, let's just imagine that we pick some equal grid size. So delta x is equal to delta y. I'm just trying to make this as simple as possible, and then we're gonna work on an Excel file. So in this case, actually, I can divide all the equations with kx and with delta x, and the final form, well, this will be cancelled, this will be cancelled, and the final form is an interesting form. U, I, and j, which is my center point, will be the average of all the adjacent points. Okay, so adjacent points means ui plus 1 and uj plus ui minus 1 and j plus ui j plus 1 and ui j minus 1. And this is an average, so divided by 4. I just substitute kx with ky and delta x with delta y, and then divided all the equation with ky and delta y. So again, the meaning of this is that if I'm trying to find out my unknown function for the center point, I need to have this point on A the point on left, the point on right, and the point on the below. And this is just taking an average from all these 4 points, right? Does this make sense? Okay, good. Let me borrow this form. We're gonna need this. One more page. Boundary size. Okay, let's say we have a very simple problem. I'm gonna have a column of soil, and this, let's say this is filled with soil. This is like a permeability test, right? We're gonna fill some tube with soil, apply some total pressure on one hand, and then release the water from the other hand and see what would be the velocity or permeability of the system. So let's say in this case, I'm gonna connect the left boundary to a tube, and then I'm gonna fill this with water up to some special point. So in this case, let's say this is the total head from my inlet, and this is known, right? For the other hand, this is an open boundary. So this is my total head at the output, and this should be equal to 0 because this is open boundary. The water can freely move out from your boundary, right? So remember that this open boundary is different from what we define in our 2D advection or diffusion boundary, right? In our 2D advection diffusion problem, we had some pollution. The open boundary here means this boundary, this is just a small boundary of a really larger one, right? So we're gonna just assume that my pollution can escape from my initial domain. This is totally different from what we defined here, right? Okay, so the total head should be equal to 0 because this is exposed to the atmosphere, right? Okay, so let's see how we can actually solve this Laplace equation for this simple problem. Let me create a grid point along my domain. My domain is just inside my soil, right? I don't care about this tube. This will just give me the information of the inlet total head. Let's see what we have. I'm gonna discretize this in X and Y. For the Y direction, let's say 1, 2, 3, 4. So how many? 3, 7 grids, right? And then we can actually create the same thing for the X direction. So this is my grid. Okay, can you tell me what is the initial condition? Let me give you some number. The H in this case is 2 meter. This is my total head, and H out 0 meter. So which points on my grid is going to have some initial condition?
Points on the left, along the left side.
Almost, but actually I had, this is not initial condition, okay? So the answer to this is that this problem doesn't have any initial condition, and why?
Steady state.
Exactly. Thank you. So this is a steady state, right? Initial condition means all the values for the first time interval, right? We don't have any time interval, so there is no initial condition. But what is the boundary condition? So as you said, one of the boundary condition or BCs is about the points on the left, right? And then these are known because the unknown function of our Laplace equation, which is the total head of all these points, would be equal to 2, right? This is all known. What is the other boundary condition? On the right-hand side, right? And these should be all equal to 0. Okay, what is the discretization scheme? We have to use this guy, right? So for each point, we're gonna borrow the value from left, right, above, and below, take an average, and this will give us the unknown function. Am I missing anything here? Is there any other boundary conditions?
Top and the bottom.
Exactly, and what would be the condition for top and bottom?
You just double the term that's below the top. In other words,
Okay, you mean double B?
yeah, instead of L plus R plus A plus B, maybe L plus R plus 2B.
Okay, and can you tell me why?
No, intuitive.
Okay, you have a great intuitive mind, I would say. That is great, thank you. Yeah, exactly. But then if someone can tell me the reason, there would be 2 extra points for your final grade. So let's just think about the physics of the top and bottom boundary a little bit. What is special about these 2 boundaries? This is a closed boundary, right? But then what does that mean?
Does that mean it's variable?
No.
No mass can transfer across it. There's no
Exactly, okay.
clean flow.
Exactly, there is no flow in this direction, right? I mean, there would be a flow, right, slipping on my surface. This is fine, but then there wouldn't be any case like this. Was that Sean or?
Yeah,
Yes.
it's
Okay.
someone else.
Okay. So this is not possible, right? This is a closed boundary. This cannot be happen. This is not the answer that I would like to. I mean, that was nice, but this is not the final answer. Right, we have to find out. Okay, so Sean said it should be for these specific points, right? On my boundary, I should write like this. Let's say, I'm gonna just simplify this, right? So I have L, R plus A plus B divided by 4. But then instead of having this above point, I'm gonna just put a B, another B. But then question is why? I briefly explained that this is a closed boundary. If you have that answer, you can tell me.
Because the point by the point on the closed boundary will be the same as the point below.
Okay, could you repeat it, please? Say again.
The point on the closed boundary will be the point below. will be equal to the point below.
Not really. No. No. This is not the answer, right? So I'm trying to find out what is special about the physics of this point, right? So this is a closed boundary. I said, okay, there would be no flow perpendicular to the boundary. This is the case, right?
Yep. So you're saying since there's no flow across it, there can be no loss of potential. So if there were a point on the other side of it, it would be the same.
Exactly. Yes, almost. Yep, almost. So this is a case basically, no flow perpendicular to the boundary. And this means that there would be no change in my unknown function, which is my total head, or u, in this direction, right? Or perpendicular to my boundary. And what is this change means? This means in terms of derivatives, right? This means that round u or du over my dy, because I'm talking about this boundary, so there would be no change in this direction. This should be equal to 0, no change, right? And that's about a closed boundary. But then why we have this b? Well, I have not received the final question. This is a little bit tricky. We did not actually use the central scheme in our previous problems, but this is actually when it's very useful. So can you tell me what would be discretization of u with respect to y, I mean this guy, in central scheme?
The uj plus 1 minus uj minus 1 over 2 delta
That's right.
y.
J minus 1 over 2 delta y, exactly, right? So this should be equal to 0. So this is a discretization because there would be no change in y direction. This should be equal to 0. And then what does that mean? uj plus 1 would be equal to uj minus 1, right? So if I zoom in right here, let's say I like to calculate a value for this specific point. For the approximation, I know that I need to have these 4 points, but because this line is a special boundary, it's closed. And by looking into this no flow condition, this guy will be exactly equal to this below point. So we don't need this point. We're gonna just double the below point. Does this make sense? Good. I hope that this makes sense. What about the other boundary? What would happen to this case? Well, of course, you're gonna actually double this point, right? This should be doubled. So there are 2 boundary conditions in this specific case. Any question? Okay, so let's work on some more complex boundary condition because we're gonna just have 15 minutes. I don't want to go into the Excel file. We can start next lecture, but let's work on some other problem. Let's say I have a concrete dam. This is all concrete. This is my ground level. Or let's say this is my ground level. So it's a little bit pushed into the soil. My upstream, a little bit of downstream, and this is all my soil. This is bedrock, no permeable or impermeable. So one of the boundary conditions would be, of course, this line, right? This is closed. And this means the water cannot flow perpendicular to my boundary. Can you tell me the other boundary conditions, the closed boundaries?
The bedrock, of course.
Yes, so here and here, right? Good. So let's actually discretize the system. Let's say this is my ground, my concrete, and this is ground, right? So I'm gonna discretize this with some grid point. Again, this is all concrete. As this is not soil, no need to discretize the concrete. Okay, so these are my grid points. And these are my grids, right? So we already talked about the boundary condition on these special points. And then the form would be L plus R plus 2B divided by 4. Okay, question. What would be the formula for this specific point? For the blue line,
2R plus B plus A.
exactly 2R plus B plus A divided by 4. And for the left side, it should be 2L plus A plus B divided by 4, right? Actually, there are two more special points. Can you tell me what are those points?
The corners.
Exactly. So these 2 points, actually, these shouldn't be red. These are some special points right in the corner. And can you tell me the equation for the corner point on the left? These yellow points. This one. What would be the equation for this corner line point? So for this guy, there would be no flow in this direction, right? And no flow in y direction. How to approximate this? Still waiting. It should be easy, right?
What? 2L plus 2B over 4?
Yes, exactly. 2L plus 2B over 4, right? Or let's say L plus B over 2. And for the other guy, the same thing, but in other direction, right? So this one should be 2r plus 2b divided by 4. So in this case, you can define all the boundary conditions which are closed in your C page problem. Okay, what is different from 2D advection and 2D diffusion is that those problems are time dependent. And what is specific about this Laplace equation is something that I'd like to explain here. Let me see if I can. Okay, let me draw one more grid point. Just for a simple problem with a few grids. Okay, so let's say some points they have known pressure heads or total heads, right? These are knowns. We're going to start from the very top, this guy, and then try to calculate the unknown function, right? So what would be this unknown function? I'm going to use the value on left, right, and 2 times from the bottom. Let's say this is a closed boundary. So can you tell me what is wrong with this calculation? Why I cannot calculate this value?
The ghost points.
There is no
On the
ghost
left.
point. There would be no ghost point. For this black point, I'm gonna use just left plus right plus 2 times below, and then divided by 4. But then why I cannot calculate this?
What's the value of the right point?
Exactly. So because we don't have any value for the right point and for the below point, right? The left is known, but not the right and below. So what we do for this Laplace equation kind of solution, we're gonna just put some initial values, some artificial numbers, right, into the unknown points. So at the very beginning, I'm gonna just fill all the points with whatever, let's say 0, right? And then so on. For this black point, I can actually update the value, right? So let's say I'm gonna update this this is update 1. It will give some value. Let's say if this is 0, the left side, I put 2 for all the points. And these are known, so this should be 0. So what would be the value for the black point? Left plus right plus 2 times below divided by 4, right? So right is 0, below is 0, and left is 2. 2 divided by 4 means it will update to 0.5, right? We're gonna move to the next point. So when we move to the next point, actually the left point has updated. So what would be the value for this point? Can you update this point?
.25.
Point, not exactly.
Point 125.
Exactly, it should be 0.125, right? So it's L plus R plus 2B divided by 4. So these are 0, this should be 0.5 divided by 4, right? So in this kind of marching, I can update all the values, and then at the very end, when I reach to this point, I have the first sets of updates, right? So let's say by the first iteration, so we call this iteration, and this doesn't mean any physical meaning in terms of the time. These are just you know, approximation iterations through your physical points, which it's a steady state, there is no time. So let's say at the end, I'm gonna have 0.5, you know, 0.125, and I think it will be decrease again. And you're gonna have some other values for these points, right? Some new values. So can you update this point again? Well, this will be updated again, right? If we go to the next iteration. And why? Because this point, this is also updated. In previous stage, this was 0, right? Before update, before the update. And this is also has updated. So by iteration and iteration and iteration, at the end, we should get some results with very accurate, you know, approximation. So how to set this iteration, how to find out the number of iterations is actually coming from the changes of your values, right? So after each iteration, these unknown values would change. So how to set the criteria and how we can find that the result is accurate? Once the change in your unknown function reaches to certain error, and you can set that error, then you can stop the iterations, right? So for example, I can say if the change in my unknown function in each iteration is less than 1%, let's finish the iterations, right? So for example, for the first point, at first iteration, I got 0.5. I'm talking about this point. In the second iteration, you got 0.4. So what is the error in this term? So the change is 0.1, right? 0.1 divided by the initial value, which was 0.5. This is about 20% change, right? And this is not acceptable. So you can set the change to be less than 1% or even 0.1%. And then once you reach this value, then you can stop the iterations. And we actually will do this on Excel in the next lecture. Does this make sense? Any question from the iterative approximation scheme in Laplace equation? Okay, so let me define the two examples so you can work before the next lecture. So we're gonna actually make Excel file for two examples. Example 1, we're gonna have a soil column. It's exactly like what I explained. This is open and this is open. We're gonna have a total head of about 100 in the left hand side. Let's say we're gonna have a column. Fill this with water. So constant head. And h is 100 meter. So this is a pretty big problem. This is 20 meter, and the length of my column, it's about 100 meter. Sorry, 40. So L 40. And h is equal to 0. This is an open boundary condition. This is my soil. And above closed condition, this is also closed condition. Let me see. Okay, let's define delta x equal to 1 meter and delta y 1 meter. So this is all you need to have for example 1. Example 2. This is a little bit more challenging. So almost the same thing. For this case, we're gonna close the right boundary. Okay, and we're gonna open up a hole. This is 5 meter. This is also 5 meter. So just by intuitive feeling, you can say that we're gonna have some flow in this direction. For the other case, we're gonna have some flow in this direction, right? So the question is, what would be the pressure H for all the internal nodes in your soil? And then once you have result, let's plot the contour of H. And this should be just done in Excel. And if you have time and interest, let's just plot contour of H. Yeah, I'm just trying to work on Excel first, and then we move on to MATLAB. I think I defined everything. Yeah, this is all you need to create your Excel files. Any question? Okay, so like what actually Sean gave us the demo for his work, I would like to have more participation in the next lecture. So let's see if somebody else can give us a demo for her or his Excel file. Okay. Great, guys. So if you have no question, then I'll see you on next week. Thank you. Thank you.
Dr. Mahabadi?
Yes.
I did something like this a long time ago in my undergrad. It was actually a senior project, and it was like, I think I had to use Excel to plot the water potentials in a soil that had a drain. And it was, I think that's where I got that feeling that the other point is just equal to the one on the other side of the boundary. I think I remembered that that was how they told us to do it. It just sort of makes sense. It just seems right. I don't know why.
Right.
Now I know.
Right. Cool. Yeah, good to know. Exactly.
Yeah, we did it in an Excel, and it would take forever to do it. I don't know. Now computers are a little better, but you have to walk away from it. Just let it.
Exactly. Yeah, but actually Excel. So if you search on Google to how to actually use iterative kind of calculation, Excel has nice capabilities. So it's not just copy every grid and calculate each iteration. It can actually make the iterative calculation automatically.
Mm-hmm. Yeah, I kind of remember that.
Yeah, I think it's gonna be a nice experience before going to the MATLAB. So you get all the boundary condition, and once you're comfortable, then we can work on writing the code in MATLAB.
Okay.
Yep.
Cool.
Nice. Thank you.
Thanks. Yep. All right.
Thank you. Have a good night, Adam. Thank you, Prasanna. Have a good night. Hey, Sina. No questions, Sina?